So most of you are probably familiar with generative AI, particularly with the advent of ChatGPT less than 2 years ago. The core of that is large language models, which is actually a little bit different than the ML per storage stuff that we just saw. Those are mostly older categorization and other types of models. So the models for generative AI have been getting bigger and more complex for actually several years, reached an inflection point about 3 years ago. And the systems needed to drive that, including the storage, are getting bigger, more complex. One of the things we wanted to talk about today is what do those I/O patterns look like? Because that informs, well, how do we build storage platforms to support the big compute systems? And then also we're going to talk about the security aspects, because that's increasingly important for all the work that we do, both for AI and for other traditional modeling simulation workloads. So we're going to talk about doing that and how we sustain performance while adding security. First, a little background on the systems that Aurélien and I work on and that we used to support the work that we're showing today. So our group supports multiple purposes. So we do early system checkout and Q&A before you guys all see the hardware. We do scale testing, continuous integration of our internal software, and then also large-scale AI training like what we're talking about today. One example system that's been publicized is the EOS supercomputer, hit number 9 on the recent top 500 list. Yeah, that's Limpact. We do training, but still, it's a fast machine. So the system that we actually worked on recently is basically a smaller clone of that, replicates all of the key features, in particular for storage, the dual rail NDR InfiniBand. As for the storage itself, it was based on the DDN exascaler platform. We had 12 appliances, so that's 24 controllers. And when you add it all up, it gets about 1 terabyte per second of bandwidth, which is far more than we needed for our test today. So I just want to put that out there that any limitations that you see, any caps in performance was not driven by the back-end storage. So we're looking at what are the clients doing. As for the Lustre version, we used a 214 base with DDN's exascaler patches and then some of our own work. We use persistent client cache that's available to our users on demand through a Slurm hook. We use project quotas. We have a default progressive file layout set up. We use subdirectory mounts to help with data management. And then Kerberos is fully integrated into the system to improve security. And we're going to talk about that a lot more later. As for the particular application that we focused on to kind of showcase and look at the I/O patterns, we use the Megatron LM. It's a framework. It's open source. And the key aspects of this, it's 340 billion parameters in the model and an 8 terabyte data set. So it's pretty big. It's about 20 times bigger than the last time NVIDIA showcased some work on PCC at LUG a couple years ago. As I said earlier, things are getting bigger fast. If you want more information, there's a link on the slide to what that model is. But for now, we'll dive right in to the I/O profiles of the codes.
So as Nathan explained, this is a real application, not something benchmark here. And so the idea is to have to try to understand a bit better what this kind of application, how it does I/O. So the first thing we are looking at right now is the general trend of the application on the compute aspect and I/O aspect. And what we can see here is there is several phases. The first thing on the compute aspect on the left is there is some startup phase, some init phase, and then we have a sequence of compute, pause, doing I/O, compute again, pause, doing I/O. And if you've been working in HPC field for a while, you probably recognize that as a typical HPC pattern. This is not something really different from what an HPC application could be doing. In that case, with compute and checkpointing and repeat until the end of the program. If we look more, especially on the I/O patterns, so we see that there was a startup phase on the left, and we see that during this phase there is a high peak of read, which is around 75 gigabytes here, and then there is this compute and write phase, and on the compute part it looks like it's quiet, like almost no I/O there, and then the write, high peak of write, which is basically the application checkpointing, and repeated that again. So yeah, as I said, quite typical HPC pattern, suboptimal checkpoint. The application is in pause mode during that, so maybe there is room for improvement, but nothing very surprising so far. And by the way, applications are using buffer I/O. If we zoom on the compute phase, so same graph on the top right, if we zoom on the compute aspect and on the read actually only, we can see that actually this part is not that quiet. It's just, there is a constant stream of reads. It's just that they are really low. This is mostly small I/Os, less than a page in size. And bandwidth is basically scaling with the number of nodes which has been involved in the test, which was 48 nodes, 48 clients for that run. On the far left, this is still the startup phase, the large peak, but as this is zoom, it's truncated. So one interesting thing here, from what we've seen, it's there is very little read actually being done for the application, and and what drives most of the bandwidth is actually the write. The read, even if they are steady, are really low. If we focus on the write now, so what we've seen in the first slide was that basically there is compute phase and a pause. And during the pause, application is writing, so application is basically checkpointing. And on the compute part, the GPU are likely busy waiting for the checkpoint to complete. So faster the checkpoint will be, better it will be for the overall runtime. And if we look at the checkpoint in details now, so for that run, the checkpoint was roughly 4.3 terabyte in size. And here, only some of the nodes are involved in the checkpoint. This is based on the model parallelism of the application, how the model is designed. And we have spike up to 75 gigabytes, which means that each client was writing at roughly 6 gigabytes per second out of the 93 gigabytes available for those nodes. As Nathan explained, we are not limited by the hardware here at all, more by how the application is actually using it. And checkpoints were lasting for 90 seconds. So here, scalability is driven by the model parallelism and not by node count. So then we try to look at that simulating. So now this is synthetic. This is no more the application. Actually looking at the checkpoint aspect of the application. This is based on how the application is working to parallelize the checkpoint itself in order for it to use all the available nodes. So now all the 48 nodes will be able to write a part of the checkpoint. And on the graph, we see 10 successive checkpoints being done by this code. And we see that there is a large speed up when all the nodes are actually involved in the checkpoint now. The peak is at 275 gigabytes here, 4x speed up, and it's basically 4x more nodes being involved in the checkpoint. So there is definitely room for scalability if you increase the node count here because every node are involved, and that scale quite well. The only limitation here is this is still synchronous, and there is it would be good to have something more asynchronous on that aspect. So takeaways for that part is very low read bandwidth. So this kind of application are no read intensive. You can have a focus on small I/O, but I don't think that's really a problem here. And all the write phase can benefit from the hardware if you thanks to the parallelism actually. And in that case, you will try to exploit whatever hardware you have on the client and servers. And improving checkpoints actually speed up that a lot, and then probably room for improving that even better. So now Nathan will talk about the workflow aspect of that. We'll come back to performance after that.
Great. Yeah, just to give a little context on how these applications are run on our system. So we use a CI pipeline for a lot of the work on our system. Not all of it, but a lot of it. We find that both the users like this for their applications and their own continuous integration work, and then our admins also like it for continuously making sure that the system itself is operating at peak performance. So generally, to just kind of walk through how this works, we're based on GitLab. A CI job will be triggered out of GitLab, either user doing something in the GUI, that we have a little mock show up here, or a trigger based on an event or a timer. That will start the pipeline by a runner node, which is a dedicated server or VM that kind of acts as a hop between the corporate GitLab instance and the cluster that we manage. That will connect to the cluster and submit a batch job. In our case, we're running Slurm. That will just run as per normal scheduling and then eventually get launched, access Lustre, all the good things there. Generally, that's been working well for us, although there are some challenges and some security and manageability aspects that we wanted to improve. So historically, the connection from the GitLab side of the house, where it was managed under the kind of the corporate IT umbrella and their set of accounts, and the cluster, which was its own security domain, that provided a difficult interface. And so we just used SSH keys because they're ubiquitous to allow access into the cluster from the runner node. SSH keys do come with problems. You can't really guarantee who's using it. Like somebody had an access to the runner node and launched something via the CI pipeline, and they could get a key, then they could run a lot of stuff on our systems. Not the best. Also, they're not easily revocable, and the manageability around these two different account types kind of encouraged our admin team to gravitate towards a shared account for CI. So bunch of users could submit to the CI pipeline. It would connect to the runner and then use a single account on our system. That meant for them to go back and look at the data that was generated on the system. Sitting on Lustre, we needed pretty open permissions on that. And again, not the best security practices there. So what we wanted to do is really reconcile the GitLab, the corporate IT side of the house with our internal systems, and then provide strong authentication that the person connecting from the outside to run through the CI pipeline was actually who they said they were. So we needed to change our authentication method on the cluster itself, and Aurelien's going to give you good details on how we did that.
So in order to do that, we are actually looking a lot and deploying kind Kerberos, actually, to try to improve all the general security posture we have. So before going to the details, what's Kerberos? And Kerberos is actually well-established authentication protocol. It supports modern cipher suites like AES or NSHA-2. Actually, it is widely deployed, especially, by example, if you are using Active Directory, maybe you don't know, but under the hood, Microsoft servers are using Kerberos a lot. And Kerberos architecture is using a piece which is a KDC. So I'll try to simplify that a bit. And this KDC centralizes everything. And on the KDC side, you will actually manage the identities like users and services, a credential for them, which could be a password or a key tab, and you will put that in a domain which Kerberos called a realm. And so if we look at the slide, we can see that we have some clients where with users, the users can authenticate to the KDC. KDC will give it a ticket, and this ticket will be provided to different services which are also using Kerberos. And those services will be able to authenticate the users thanks to the ticket instead of having to use the actual user password or things like that. And what good thing with Kerberos also is that each service also has its own credential. Here, a key, which is the key tab. And so the services could also authenticate each other. And here, there is A and B could ensure that they are who they claim to be, and add some additional layer of security thanks to the key tab. And all of that is validated thanks to cryptography. So the benefit is you have everything in the same place, everything in KDC, it's either from a management standpoint. You have single sign-on features thanks to the ticket the user is able to get, and you can present that to any service. And service and host can be authenticated. And they can authenticate you. I already said that. So if we look at how this applied to Lustre, so as we said, there is increasing need for better security and integration. So Kerberos is one way to do that. And actually, when you deploy Kerberos with exists for a while, what could have been done in HPC Center is to do that more only on the login nodes, coming from the outside world, maybe connecting to some Active Directory. And then when you are inside the cluster, you are a bit more wide open in terms of permission, and you are using more traditional way to do a security check. But what we are trying to do is actually to deploy Kerberos everywhere inside the cluster and apply that to every services, which include Lustre. Lustre, even if it's changing a bit on the recent version, but more generally trust a lot what the client is doing. So when a client try to mount the file system, the servers will trust it. Trust him, it won't prevent that, or there's very limited way to check that. It's easy to still do it. And actually, we'll also trust whatever UID, GID the client is sending. So if one client is compromised, he usually has a lot of possibility to access all the file system. So adding Kerberos on top of that helped a lot to add additional way for the servers to really authenticate the client and be sure the client is who it is at connection time. And also, thanks to the ticket the user has, the servers will be able to validate that the user is really the actual user, the actual UID claims it is. So that's really interesting and really beneficial from a security perspective. So if we put back in the perspective of the CI Nathan was presenting, that means that now when your job is actually, when the GitLab and the runner wants to run a job on the cluster, the job running on the cluster will need to have a ticket to be able to access whatever service you have on the cluster. And As I said previously, to create a ticket, you need a user which enters its password to have the ticket. And the purpose of CI is really to do this non-interactively. So there is no user to enter the password. So no, you now need a way to get a ticket independently of the user. And for that, we rely on an open source tool we developed, which is called Sibyl, which will be deployed on the runner and will be able to impersonate a user to fetch a ticket, a short-lived ticket, just for the time of the job. That will be provided at the same time of the job, and thanks to that, the job will be able to run on the cluster. And so we'll have all the benefit of using the actual user ID and instead of a more generic service account or more generic SSH key. You have better control on the KDC. You can revoke permission more easily when user is compromised for some reason. But the difficulty was really how to handle the ticket, and Sibyl is the way we fix that. If we are digging deeper now into how Lustre and Keros work together, and we look a bit more on some features, there's different Keros flavors you can enable in Lustre. And actually, the Keros flavors are enabled per connection, which means that you can have different flavors. For example, here, with the client to MGS connection, there is one flavor. Client to MDS and OSS are using a different one. And servers, when they are talking together, are also using a different one. So what are those flavors? So the first one is null, which basically means no Kerberos. This is what everybody's using by default. And then the first actual Kerberos flavor will be KRB5N, which is authentication. So authentication is everything I was explaining before, where really the Lustre servers and clients will authenticate each other. Mostly the servers will authenticate the client and the servers will authenticate together. And on top of that, you could add additional layer of security. You can add checksumming with the integrity feature with KRB5A or I, so the yellow and the blue. A will add some checksumming only on the RPC header, and KRB5I will do that for the whole RPC. And encryption could be also added with a privacy feature, in that case, the flavor KRB5P, and in that case, the whole RPC will be encrypted. And it seems likely that adding that, cryptography things, checksumming, or encryption will have some performance impact. So let's see. The first benchmark I run here is an MD test on one client, even if it's one client, comparing the different Kerberos flavors available. And the first thing we can clearly see here is the performance impact is quite limited. The difference between the different flavors are not huge, on the same range for the different kind of MD tests. And they are all in the 4-10% maximum difference between no Kerberos and encryption, except for file removal on the right, which has a wider range, which are more likely test artifacts than a real difference in behavior in the Kerberos implementation. And so that's a good thing. You can enable Kerberos for metadata pretty easily at an affordable cost. And you can probably pick whatever flavor you like. And KRB5N authentication is quite cheap. If we look on the bandwidth side, so for read and write, and if we start to compare with KRB5N, so the first level of Kerberos authentication, on the green and no Kerberos, the purple, we can clearly see that for this one client, read and write are not impacted at all. And we are in the same range of 91 gigabytes per second for that client. And it makes sense because OST don't do authentication per RPC, but mostly at connection time. So once you're connected, you don't do any more heavyweight Kerberos processing. So that's why there is no impact here. If we now try to compare with all the other Kerberos flavors, in that case, I try to see how it scales with 65 clients with a different kind of flavors. So the green one on the top is still KRB5N, so only authentication. And then successively, we can add more and more security with KRB5A, I, and P, so checksum and encryption. And we can see that the impact is huge, especially when you go up to full encryption, where we have 85% performance drop. And actually, most of the time is lost in the crypto function used there. I did not have time to really dig into that, but it would be interesting as a follow-up to see if there is a way to optimize that using different algorithms, or if there is better implementation for those algorithms with probably more hardware offload, to see if we can get something a bit better. But in that case, performance impact is too huge, except for KRB5N. And so we don't really recommend using them, except if you are, it's unlikely when you are using Lustre that you are fine to pay this price here. So on the conclusion for that, we've shown some I/O profiling of a quite typical LLM application, which shows that there is very little read going on except at the beginning, and most of the I/O challenge is on the checkpoint and on the right. We also show that we can improve security over there thanks to Kerberos without impacting the performance as long as you stick to KRB5N. On the metadata side, you can go even deeper, but already KRB5N gives you a good result with very limited impact. And all of that could be done efficiently through a CI without having and taking in account all the constraints as those additional security layers could be added. And this could still be done without having to change that. So we can have the CI working well even if you are doing Kerberos, for example. And at the end, I would like to thank Xiaonyang, one of colleagues, for all the help of collecting the LLM I/O data, and Sebastian, Andreas, and Peter for the support and help in improving Kerberos stability. Do we have questions?
Kevin Harms, Argonne. Yeah, I've got a few questions, so I'll give you them one at a time. So for the, I'm not as familiar with using Kerberos. So it happens when you mount or when you open the file. When is the ticket provided?
Yeah, so there's two things. Connection time, so mount, or any reconnection, which could be happening after failover or whatever. So this is fine because it happens only once. And on metadata server, you will have validation of the user ID for every RPC, or every RPC which implies UID. So that's why it is more difficult here, but results are quite good.
Okay, and then a couple questions on the performance. So in the performance data that you showed, was that collected based on is that measured at the server side, at the client side?
For Kerberos?
No. So, well, for the large learning model.
Okay. I forgot to mention that. So we use Prometheus and Grafana to collect a lot of stats, and we pulled out of that. So that was collected
Mostly on server side.
Mostly
Server side. Okay.
Yeah.
I guess I was interested if the reads are getting a hit rate, if they're reading out of cache, or if there's actually more demand, but it's not making it to the server, or if it's really just that sustained trickle.
Actually, based on what I understood of the application IO pattern, I think each read is really reading a part of the dataset, which is a different one each time. So I don't think cache is involved here. Thank you.
Let's give another round of applause.